Hello everyone, welcome to lecture 28 of the course Diffusion in Solids. Today what we are going to talk about is something called Kirkendall Effect, and we are going to define what is meant by the intrinsic diffusion coefficients. So, these are the key words, and so far what we have talked about in interdiffusion process is, like for example, you have two elements, you make a diffusion couple, you anneal it at a temperature, at a certain temperature for duration, and then you can see several phases growing in the interdiffusion zone. We have seen several examples where multiple intermetallic phases grows, or you have solid solution phases growing, and so on. Here I have just represented a very simple case where a solid solution phase grows in the interdiffusion zone, and this is the kind of composition profile that you get. Now, for such a scenario, we also seen that you write dou C by dou T is equal to dou by dou X inside d tilde dou C by dou X, because you do not have the interdiffusion coefficient independent of the composition. So, therefore, this cannot be taken out, and therefore, the equation is no longer ordinary differential equation, but it becomes a nonlinear which cannot be solved simply. And in the last class we also saw using the Metano-Boltzmann analysis how we can arrive at the expression for interdiffusion coefficient. So far we have talked about only one interdiffusion coefficient, which is d tilde, which gives the rate of intermixing of A and B. That means, A and B are mixing, and we are trying to see at what rate this intermixing is happening. We have defined only one interdiffusion coefficient, and we also emphasize that there is only one interdiffusion coefficient for a binary diffusion couple. You do not have a d tilde A and d tilde B. You have a d tilde A B sometimes you write, or you just write d tilde as far as the binary diffusion couple is concerned. Now, we saw that one of the approaches to determine this d tilde is the Metano-Boltzmann analysis. But what about the individual diffusivities of A and B? See, even in the intermixing process, there is a movement of A, there is movement of B. So, are these diffusion coefficients equal? Are these elements moving at a same rate? So, what about that? So, that is what we are going to see in the remaining lectures, and what was observed through the Kirkendall effect. Even before the Kirkendall effect, people tried to take hint from some of the phenomena that is observed, and to see whether in such a scenario do you get the dA and dB to be equal, or are they different from each other, or if they are different or same, are they same as the self diffusion coefficient, or their values are slightly different. So, this we will try to understand in today's and in the next lecture, that what are the individual diffusion coefficients that are concerning here. So, before I go to define this word intrinsic diffusion coefficients, let us just recap quickly what have we studied before. So, what we have used the term something called as a self diffusion. What is self diffusion? That is the diffusion of A into its own lattice. Okay. So, we are right now only talking about the substitutional diffusion, or we are talking about the diffusion through the vacancy mechanism. So, the diffusion coefficient of A in pure A, or the diffusion coefficient of A in the alloy of A, is what is known as the self diffusion. It is having no particular force, driving force as such, and this is purely based on the random motion. So, this is what is known as self diffusion. So, the diffusion coefficient is the self diffusion coefficient. When you put a radioactive isotope of A, either over a pure A or over an alloy of A, and you measure this diffusivity of the tracer atoms, that you define as the tracer diffusion coefficient. So, this is tracer diffusion coefficient of the tracer of A in pure A, or you define tracer diffusion coefficient of A for an alloy A. So, how fast the radioactive isotope of A is diffusing. We will also see that we cannot directly measure the self diffusion coefficient. So, the closest we can measure is the tracer diffusion coefficient, but these two are slightly different. Now, there is one more diffusion process that happens that just now we talked about, that in the interdiffusion scenario, for example, you have a block of A here and you have a block of B here. These atoms are moving across the interface, as well as to reach the interface they have to diffuse within their own lattice. Now, you see there is a one difference here and here in terms of the driving forces. So, in the first case, when it is a self diffusion, it is no driving forces present. In the case of tracer diffusion, it is purely entropic driving forces. There is not enough concentration gradients or so on that is present. But here you have a very large, or rather I say relatively large concentration gradients that are present, or as we saw in the chemical potential lecture, that the diffusion is driven in this case by the chemical potential gradient. So, you have a pure A here, you have pure B here. So, that is what drives the diffusional process or the interdiffusion process. In this scenario, in this scenario, when there is a driving force present, how fast the A atoms are diffusing is what is known as intrinsic diffusion of A, or intrinsic diffusivities of A. So, whenever you define the word intrinsic diffusion, inherently you are implying that there is a chemical driving force present. So, the diffusion of A with no driving force is what you are referring to as self diffusion. That means diffusion of A in pure A or in alloy A. When it is purely entropic driving forces, then you call it as tracer diffusion, or here it is the diffusion of radioactive isotope of A. It need not be actually radioactive, it can be any other isotope of A also. And then there is a third scenario when you have a relatively large chemical driving force present. In such a scenario, how fast the A moves is what is known as the intrinsic diffusion coefficient. Okay. So, I will just give you a very simple analogy also. Suppose if there are a lot of kids in one room, they will be moving randomly here and there at some particular speed depending on the kid, and there is no real driving force present. They just randomly, due to their own nature, they will be moving across the hall in random directions. Now, imagine you put a table at the far end of the room with a full of chocolates and toys. What you will see? You will see that the lot of kids will move towards that table at a speed which is different than what they were previously moving. So, that is the kind of influence that the driving forces have. So, the speed at which they were moving before and the speed at which they move now when they see the chocolates or the toys are different. Similarly, in the atomic movement also, when you have a driving force which is present here, the movement of A or the movement of B becomes different than when it was a purely random motion without any driving forces. So, this is the basic difference between the self diffusion, tracer diffusion and the intrinsic diffusion. So, just to recap, the tracer diffusion and self diffusion are related as D star is equal to F into D self, where F is the correlation factor. And subsequently in the next lecture, we will also see that how this intrinsic diffusion coefficient and the tracer diffusion coefficients are also related. So, that was about how we define the intrinsic diffusion coefficient. Another question was whether these intrinsic diffusion coefficients of A and B are equal or not. So, people started observing some hints. For example, when iron or a steel piece is being oxidized, there is an oxide layer here forms, and let us say if some muffle pieces, some particles fall on these oxide surface, what people observed that over a period of time of exposure, these pieces get buried under the oxide layer. And when do these pieces get buried? When will they get buried? Suppose if the rate of movement of iron and oxygen were similar across the interface, then they will not get buried actually. So, this indicated that the diffusion rate of the species iron and oxygen are most probably not the same. Then in 1947, Kirkendall with his student Schmeichel class, they designed a special experiment. This was published in 1947. So, what they did is, they took a rectangular block of brass, which is a copper zinc alloy, and they wound this block with molybdenum wire. Following that, they electroplated the block with pure copper. Then this block was annealed at an elevated temperature for different times. So, this is shown here. So, this was the brass along which they put the molybdenum wire, and it was further coated with copper. Now, this assembly, so you can see here the outside is copper and this is brass, and these are the molybdenum wires. So, this is a cross sectional view, and this was heated at a temperature T for several different times, and what interestingly they observed, this marker position actually started changing. So, you can see here after T1 the marker is here, this brass region is actually shrinking. Then if you heat for a further longer duration T2, the marker position changed further. So, the brass piece was shrinking. So, this was a surprise because they did not expect this movement, this marker shift to occur, and they observed that with annealing time it moved even more. So, why it was surprising? Because if the diffusion rate of both the species were same, that means if the copper and zinc diffused at the same rate across this marker interface, then you will not see any any movement of the marker. And actually, if you remember, when we talked about the atomic mechanisms, we talked something about the direct exchange mechanisms or the ring mechanisms. There, if a direct exchange mechanism means that A and B should move at the same rate. Similarly, for the ring mechanism. So, for a long time actually people thought that defects do not play a role in the diffusional process. Okay. So, the thought of the vacancy mechanism was there, but nobody had a convincing result about it. Now, this experiment actually showed that the rate at which the zinc and the copper move are different, and if they are different, that means they cannot be moving by a direct exchange or a ring mechanism, because that would require the equal diffusivities. So, there has to be a defect playing a role in this kind of movement. So, the molybdenum is actually inert to the system and moves depending upon the volume of the material transfer. So, if the copper and zinc were diffusing at the same rate, the molybdenum should not have moved. But since molybdenum wire moved towards the brass, what it means is, so you see that the brass is actually shrinking. So, brass is copper and 30% zinc. That means the zinc is moving out much faster than what the copper is getting inside. So, this indicated that the zinc must be the faster diffusing species than copper. So, and they also noted the distance up to which the markers moved, and they found that the movement of marker was parabolic with time, which indicates a diffusion controlled process. So, from the zinc copper zinc alloy, when zinc diffuses away, all the sites are not occupied by the flow of carbon atoms in the opposite direction, and as a result the vacant sites are left unoccupied. That means, the zinc atom has moved, so it has left the vacancies, but at the same rate the copper has not come inside. So, therefore, there are vacancies left. Or in another sense, if you think about it, there should be a flow of vacancies opposite to the movement of zinc. So, it would appear that as if the vacancies have flown, or people define what is known as the flux of the vacancies itself. So, I will just show you, and this ultimately leads to the shrinking on one side and swelling on the copper side. So, that markers move towards the brass side. So, this was considered as the vacancy mediated diffusion in the solids. So, you can see, for example, here the zinc flux is shown here. So, zinc is moving at a higher rate, copper is moving at a slower rate, which means that there are excess vacancies on the zinc side, which means that as if the vacancies also have flown from here to here. So, marker motion will be in this direction. So, remember that the marker motion will always be in the direction of the slower diffusing species. So, what are these markers? So, the Kirkendall used the markers as the molybdenum wires. So, but depending on the system which they are used, people can use wire or powders. So, different refractory metal and oxide powders such as tungsten, molybdenum, thorium, titanium oxide and Y2O3 are used in the metallic systems. Due to difficulty in the placing of wires, powders are most commonly used nowadays. Wires are little bit difficult to handle. So, these powders, they are actually dispersed in acetone, and a small drop is placed on the surface of one of the diffusion couple members. The surface is metallographically prepared, and after a while the acetone evaporates, leaving the particles distributed evenly on the surface. So, it is also important to note that the markers do not interact with the diffusing components, otherwise you cannot have it clearly reflected. So, the markers are made from the material which should be impervious to the diffusing components, and there should be enough space between them not to hinder the movement of the diffusing components. So, it should not be so bulky that the atoms cannot move across the interface, but at the same time it should not be so small that they are dragged along by the grain boundaries themselves. So, you should have an appropriate size. It should be much smaller than the interdiffusion zone thickness, but it should not be so small that it is dragged along. So, earlier people thought that okay, Kirkendall effect it leads to the formation of these pores. So, it will always be the detrimental effect. So, but later people found out that actually there are applications where the Kirkendall effect can be utilized to a advantageous cause also. So, it is of great interest for composite materials, coating technology, microelectronic devices and so on. And the interactions accompanying this Kirkendall effect and between the constituents of such structures can induce stress and even deformation on a macroscopic scale. It can also cause the migration of the inclusions inside a reaction zone, and it can also generate what is known as the Kirkendall porosity. See, because for example, you have this situation that you have a flux which is more on one side, which is less on the other side. So, you have a vacancy flux, and this can lead to the formation of small voids in the alloy. Depending on how much is the difference between these two flux, you can have the generation of small voids, and these voids over time can coalesce to form the larger voids. So, these larger voids, you know that if voids are present, then that can be detrimental to the mechanical properties and the overall integrity of the assembly. But People have also utilized this to make something called as core shell structures. So, you see here between A and AB, if in this particular case, if you allow the interdiffusion to happen, there will be Kirkendall voids generated at the interface, and this eventually will coalesce, and you will see that the nanosphere consisting of core shell structure is formed. Here the surface diffusion happens slowly, and these voids come together, and you have a structure something like this. Similarly, you have the oxidation of nanowires. For example, here nickel nanowires happen, where during the oxidation, because there is a interdiffusion that is happening, so the Kirkendall pores are generated, which basically again combine with each other, and you get something like a tubular structure. So, these wires get converted into the tubular structures. For the original figures, you can refer to this paper. These are the schematics that are shown here, which are adapted from the paper. So, with this we will end today's lecture, and then in the next lecture we will see now how we can quantitatively determine these intrinsic diffusion coefficients and relate it to the interdiffusion coefficients. So, thank you.